Thanks very much. It's a real pleasure to be here today, to have the opportunity to speak with you. And I especially like to thank the organizers, Tori Johnson, Robert Scott, Alan, for the tremendous work that the whole team has put together in organizing this. And I also would like to thank Suzanne for the wonderful description and the leadership that Denmark has taken in driving these issues forward. I want to talk about renewable electricity today. But first, I'm going to talk a little bit about the challenges that we face. The work that I'm going to describe at the end is characterized, some of the authors there with me are at the bottom. We had, over the last several years, over 110 people contributing from 35 organizations. And so I think it's a very interesting set of work that indicates some of the pathways that we could potentially take. First, we face very substantial challenges. Economic challenges, security challenges in terms of our dependence on foreign sources of energy, but there's also security challenges abroad because countries around the world that do not have low-cost, valuable sources of energy, that contributes and reduces their ability to economically develop, and that contributes to political instability. And we have environmental challenges, local in terms of particulates, regional in terms of acid rain, and global in terms of greenhouse gases. So what role can efficiency and renewables serve in meeting these challenges? There's efficiency in buildings, industry, and transport, renewable fuels that you will hear much about later and over the course of this conference, and renewable electricity, which I'm going to focus on mostly here. And throughout, we have to think about the speed and scale. Speed and scale are the challenges coming at us in terms of our economy, in terms of our security, in terms of the environment, and also the speed and scale that we have to respond to these challenges with. Oil futures. In the lower track there, this was scheduled to go in sequence, but since the slides are not cooperating, the first lowest line there shows the domestic supply line as estimated by the AEO in 2007. And what you see there is that our oil peaked, our domestic production peaked in 1970. As of today, that was the highest ever. Now, we have drilled 1.5 million more wells since 1970, and that was just able to keep up with the demand for oil and to keep our output slightly, just slightly declining. The second line there, new oil, shows the expected increase from the production of fracking. New oil from tight sands, from shale oil, and the rest that is being delivered by the new technologies that are just coming online. And so you can see that we get a nice bump there, but it doesn't meet the full demand. The top line shows the amount of oil that was expected to be used in, as of AEO, the Energy Information Administration Annual Energy Outlook, in 2007. Going up, going up. However, efficiency improvements, particularly new CAFE standards, have flattened that out. Now, even with that, the gap between our current domestic production and our current demand works out to be about $1 billion per day of foreign oil imports. $1 billion per day. That's almost $1 million a minute. That's a huge cost to the US economy. What can we do about that? Well, I've already indicated the opportunity for shale oil if we go that pathway and continue. We also have to think about biofuels, which many of you will be looking at closely over the next couple of days, perhaps hydrogen, electricity with plug-in hybrids and electric vehicles. We need to bring all of these clean sources to bear as fast as possible to begin to address this gap. Now, in the upper left, you can see the production of the discovery of oil over the last 100 years by decade. Those are the discoveries of giant and supergiant oil fields around the world. And what you find is that they peaked in the 1960s and have gone down since. And to give some context to that, in 1960 to 1970, the average size of new fields was about 500 million barrels. In 2000 to 2005, the studies have found that the average size of new fields was about 20 million barrels. The Energy Information Administration found that in the 1960s, there was an average of 56 billion barrels per year discovered of conventional oil. In the 1990s, it went down to 13 billion barrels per year. And the lower graph there shows what the International Energy Agency projects in their most recent estimates, World Energy Outlook, that was put out in November. And you can see that bottom dark bar of currently producing fields is dropping off like a rock. And so they project that you have to develop resources that are known but not yet developed. You have to find a whole bunch of new fields. You have to move natural gas liquids. You have to move tight oil, unconventional oil, and a whole host of other things in order to fill the gap and meet the demand that's expected over the next 20 years. What does that add up to be? That requires the addition of about 7 Saudi Arabias of oil production around the world. That's a huge task, and that's in the next 20 years. Now, what this shows is that in the first small yellow box on the left-hand side, that's how much oil has been produced. That's conventional oil. But there's lots of fossil resources out there, as you see going across. So we're not short of fossil resources. The challenges are there are some constraints. Cost, energy, it takes a lot of energy to produce many of these. Water, many of these are in areas without good supplies of water, and these are often water intensive. And finally, the atmosphere. We cannot continue dumping carbon dioxide into the atmosphere. As shown here, mostly we have focused on temperature in the past. People talk about climate change, and they talk about temperature increases, the changing climate, what that means to melting glaciers, to rising sea level, and so forth. But ocean acidification is another direct factor that comes from our increased presence of carbon dioxide in the atmosphere. And what this diagram on the right shows is from the upper left corner with 280 parts per million CO2 at the pre-industrial level. The area in blue is that area which is conducive to forms of sea life that use calcium carbonate in forming their structure. And that's not just coral, that's also shellfish, but it's also phytoplankton, zooplankton, and others that form parts of basic food chains in the oceans. And as you increase carbon dioxide in the atmosphere, Chemistry 101, some of it is absorbed into the oceans, increasing the acidity of the ocean. And by the time you get down to the lower right-hand corner there with 650 parts per million, you can see that most of the ocean is not conducive to these forms of sea life. So what happens? Well, there was a statement put out by the National Academies of Science of 70 countries about 4 years ago. They're listed there, including the United States. And what did they find? First, the rapid increase in CO2 emissions since the Industrial Revolution has increased the acidity of the oceans around the world with potentially profound consequences for marine and plants and animals, especially those that require calcium carbonate to grow and survive. The current emissions rates models suggests that all coral reefs and polar ecosystems will be severely affected by 2050 or potentially even earlier. Marine food supplies are likely to be reduced with significant implications for food production and security in regions dependent on fish protein. And finally, ocean acidification is irreversible on timescales of at least tens of thousands of years. That's ocean acidification. And two things I want you to note about this. One is a scale. It's the world's oceans. It's irreversible in any sort of human thought process timescale. And the second is they are talking about 2050. That's less than 40 years away. That is an imminent problem. A second issue that hasn't received very much attention is the issue of drought. And what this graph shows is a compilation of 22 different climate models from around the world, looking at the combination of evapotranspiration and changes in potential rainfall. Now, these are very hard studies to do, and there's a lot of uncertainties. But what you see there is in the bar graph, in the bar at the bottom, you see extreme drought at a -4. That corresponds to the Oklahoma Dust Bowl. And what you see is in the 2060 to 2069 time period, by these models, you have extreme drought across much of the United States, across much of Europe, and across much of the rest of the world. That is a problem, and that's just 50 years away on a global scale. So this is a serious challenge. Now, another one, a little closer to home, is power systems. New England has that problem today with 600,000 or 800,000 people out of power, and we've seen storms roll through repeatedly, as well as just general blackouts. That's one set of challenges, but another is just the momentary, unplanned outages that happen just briefly across the country. And we had a study done by Lawrence Berkeley National Lab about 10 years ago, and what they estimated was that those cost the US economy about $80 billion per year. Now, we've looked at how serious these challenges are. How about the scale of what we need to do in response? There was a really nice paper by Steve Pikal and Rob Sokolow about 8 years ago, where they looked at, and they divided the problem into a series of wedges, 1 gigaton each in 2050, and said, okay, what do we need to do in order to stabilize at even 500 parts per million? And they came up with this diagram indicating about 7 wedges with what they knew then could sort of pull us into an equilibrium emissions level in 2050. How big is that? Well, it would require, for example, one wedge is 1,000,000 2-megawatt wind turbines, 2,000 gigawatts of wind turbines. Now, to put that in scale, today we have about 280 gigawatts already of wind turbines around the world. So we're about 1/7 of the way there already. So great progress on that front, but we need to do this over and over and over again across these different sectors. And as indicated by the paper I've listed there at the bottom left, more recent work, published about 2 weeks ago, indicates that it's not 7 wedges to do what we need to do. We actually need maybe 17 or 18 or 19 wedges to do what we need to do. So a huge challenge in terms of what we have to mobilize and put in place around the world. And finally, how much time do we have? It takes a long time to build political consensus. As an example, CAFE standards were put into place, corporate auto fuel economy standards were put into place after the first oil crises in the 1970s. First one went into place in 1977. It was not updated until 2007. And then finally, the president, just in the last year, has put into place a 55 mile per gallon CAFE requirement on vehicles. So that's the time required to put in and build political consensus. Then you have to develop the technology, develop the production models, mobilize the finance to build the factories, penetrate the market, and turn over the capital stock. And we're looking at decades required to mobilize this activity. And we've just seen with ocean acidification, with drought, with some of these other pressures on us, they are coming very fast. So what do we do? How much can efficiency in renewables do to meet this challenge? We can look at extending current options in terms of fossil with carbon capture and sequestration and nuclear. Those are going to be important contributors. Efficiency is probably the first, biggest, most important contributor. And then renewables, both for fuels and for electricity. How far can we take them? How fast can they come into place? How well can they work? What will their costs be? What are the best pathways? These are the challenges. So first, wind. The US has tremendous wind resources, as indicated by these maps. And just to roll it up into a single number, if you combine onshore and offshore resources, fixed bottom offshore resources, we have about 10,000 gigawatts of capacity that we could tap into. The total US current generating capacity is 1,000 gigawatts. And wind is coming on very rapidly. US wind turbines installed in the past year totaled 13 gigawatts, bringing us to a total of 60 gigawatts. So it's becoming a very substantial contributor to electricity supplies in the United States. And I like to give this slide just to provide a sense of the scale of these turbines. And you can see in the lower right-hand side a Boeing 747 inside the rotor diameter of one of these. These are huge machines. Currently, turbine blades are being shipped that are 65 meters long, and companies are in the process of designing turbines that will have individual turbine blades 100 meters long. Think about the scale of that. That's enormous. Solar resources. The US has tremendous solar resources across the United States. You know, if you compare Germany, which is the world leader in photovoltaic installations today, it has the solar resources of Alaska. So the US is very well endowed with solar resources, and we are installing large amounts of solar. Our total capacity, potentially, is in the neighborhood of 80,000 gigawatts or more, and another nearly 40,000 gigawatts for concentrating solar thermal power. So we have a far, far larger resource than the amount of energy we will use. This shows the module price over time. And what you see here is prices have fallen very rapidly for photovoltaic modules. In fact, over the last 30 years, it's been nearly by a factor of 30 that costs have dropped. In fact, costs have dropped by nearly a factor of 5 just in the last 5 years for photovoltaic modules. The current market leader, I've indicated there, is First Solar, which produces a cadmium telluride cell. And they are producing in the neighborhood, a cost in the neighborhood of 75 cents a watt. There is fierce competition, including a lot of trade challenges around the world. So in 2011, the US installed about 1.8 gigawatts, and there's 1.3 gigawatts of concentrating solar thermal in the pipeline. Globally, photovoltaics installed about 32 gigawatts of power in 2012. Where are we going? Here are the numbers for Sunshot, and our goal within the Department of Energy is to drive down not just the module cost, but the entire package, all installation, all costs associated with photovoltaics, to about $1 per watt by 2020. With that, you will have unsubsidized power delivered at about 5 to 6 cents per kilowatt hour. Concentrating solar thermal. The upper left, you can see a power tower. Now, the nice thing about concentrating solar thermal is you have very efficient, very low cost thermal storage that can go with it. And that can allow the use with CSP of being able to take solar energy during the day and producing power at night. So CSP is a very important contributor to the overall picture. In the upper right, you can see the overall solar resource across the Southwest because you want high intensity, direct sunlight, no clouds, no dust. In the lower left, we have listed a whole series of filters. So it's been constrained by issues like land use, environmental constraints, various kinds of transmission requirements, making sure the land is really flat so you can build easily. And even after you go through very stringent filters like that, you're still left on the lower right with, just in this first cut, at about 11,000 gigawatts of potential generating capacity. Again, compared to the total US capacity today of 1,000 gigawatts. And finally, let me just mention geothermal. It's a very difficult one to address, but the advantage is it can provide stable power over long term. Now, the interesting thing, and the reason why I provided this slide, is totally unconnected with geothermal power, actually. Geothermal has to go through really hard rock, granites and basalts, and oil and gas companies normally drill through shales and sandstones. So that's relatively soft rock, not a problem. Drilling equipment could handle that. But with geothermal, because they had to go through such hard rock, they developed new types of drilling equipment, a polycrystalline diamond compact drill head, where they figured out how to diffusion bond diamond to a substrate material. The end result is they made drilling much more efficient. So while we're still trying to solve the technical problems on enhanced geothermal systems, over 2/3 of all oil and gas wells on the planet are now drilled with the technology that we put into place. And what does it save them? About $60 per linear foot drilled. And you have to look in the US at 600 million linear feet drilled in 2008. So that is a huge cost savings to the industry. And it just indicates, as you think about research and what opportunity it provides, research can take you in unexpected ways and provide enormous benefits compared to what the initial cost is. So this indicates the whole range of different technologies that are out there. Hydro, biomass, photovoltaic, solar energy, wind energy. How do we bring all of these together and make them work effectively in providing the power on the grid that we need? There's real challenges in terms of the variability and uncertainty of resources like wind and solar energy. And there's also new issues coming up, such as the use of electric vehicles and plug-in hybrids and the power that they draw on the grid. Can all of these systems be made to work together? So there's 3 pathways for meeting our energy future, our electricity future: renewables, nuclear, and fossil with carbon capture and sequestration. Renewables is particularly challenging because of this variability and uncertainty. Efficiency, of course, as I've said, is the underlying theme that has to be done throughout. So the study I'm going to describe briefly here, Renewable Electricity Future Study, was trying to understand how far can we push renewables into the grid, what is going to be the cost and performance, can it meet customer demands? And we looked at it with a level of geographic and temporal resolution that's unprecedented. And we've tried to find, are there synergies? Are there operational strategies that can make this work? And so the website that I give there provides all the detail. It's come out in 4 volumes. There's also, and I'll mention again later, a wonderful visualization tool that you can look at hourly simulation of the entire United States grid with high levels of renewables. So the modeling framework. In the blue box on the left, we had a number of technology teams looking at cost and performance of these different technologies. That fed into the Reeds model listed in the center. That was also supplied by the Solar DS model up above, which looked at rooftop PV systems. And the REEDS model, which I'll describe in a moment, also interacted with GridView, which is commercial utility software. And the outputs were to look at the performance of the system, cost of the system, the greenhouse gas emissions, land use, and a whole host of other factors. So the REEDS model, it took a 2-year time step. It broke the US into 356 regions with hourly resource data in each region based on, for example, 2006 meteorological year data. It rolled that into 134 power control areas, and it sliced up the time throughout the year into 4 periods: winter, spring, summer, fall, with 4 periods in each of those time slices during different parts of the day, and a super peak. Unprecedented geographic resolution, not bad time resolution, but not enough. So we also ran ABB's GridView, and that's commercial utility software used for doing commercial production cost modeling and used by utilities, ISOs, independent system operators, and others for planning their power system. It does an hourly modeling of the entire United States grid. First time it's been forced to do that. We really had to struggle to pull all those pieces together because that's a big, big problem. So it has 8,760 hours that it simulated for the entire year with realistic characteristics for each of the different plants. We individually modeled 11,000 generators, 85,000 transmission lines, and rolled those into 136 transmission zones. So all of that is crunching away to answer one question. As we go to higher levels of renewables, will the system, realistically, will the system operate? Now, some of the scenarios that we looked at, just very briefly, we looked at different levels of technology improvement. And first, we used only existing commercial technology today. And then we looked only at conservative to mid-range cost estimates. In fact, when we locked these cost estimates in about 2.5 years ago, photovoltaics has already moved below much of what we had locked in at that point, both for the most aggressive scenarios we had as well as others. And we did a series of exploratory scenarios. We didn't know what was going to happen. Is there at some point where the system will just not operate with high levels of renewables because of the large variability of wind and solar, for example? So we walked out 30%, 40%, 50%, 60%, all the way to 90% of all power on the grid coming from renewables. And we wanted to find out, did the system operate? And on top of that, we asked the question of, can we break the system? So we put very substantial constraints on different parts of the system, such as transmission constraints, or flexibility of the grid system, of the ability of other generators to provide power when needed. So with transmission, we increased the cost by a factor of 3, we doubled the losses, we limited it to existing transmission corridors, very severe constraints to see if we could break it. We also rolled in a lot of energy efficiency, considered some aspects of increased use of plug-in hybrids, and other kinds of assumptions that are listed there. First, the renewable resources are enormous, and we've already touched on that. Many, many, many times the amount of resource of electricity that's used in the United States today. And these resources are widely distributed. Across the United States, every part of the United States has substantial renewable resources that it can tap into. And we looked at these down to the hourly level. So what were the outputs? The left figure shows the baseline case with no changes. And you can see primarily reduction in the number of operating nuclear plants as they reach the end of their license. On the right-hand side, you can see the increase in renewables when the system is forced to go to higher levels of penetration, all the way out, in this case, to 80% of all power provided to the grid in 2050. Now, one of the things to note is that the darker orange and brown lines for photovoltaics and concentrating solar thermal power are not very large, and that's primarily driven because of the very conservative assumptions that we had made to begin with. Wind is very large because wind is the most mature of the technologies today. In terms of capacity, the left figure again shows the build-out of capacity, and you need more capacity because it's variable, because the capacity factors are lower than conventional power systems. And on the right, you see the amount of resource contributed by each of the technologies in terms of its actual generation as a percentage of the total generation. Now, the red line going across there is particularly important because it shows the amount that is variable generation coming from solar and wind, and it reaches nearly 50%. And just to note, the deployment is significant for all the major renewables there. There were a lot of operational challenges, and I will get into those. Now, when we tried to break the system, we put constraints on of transmission, of flexibility, of resources. And the important point out of that is that you can go through and you can look in detail and compare this different contribution by different technologies as constraints were put on the system. But the bottom line was that we have such robust and wide-ranging and diverse resources across the United States that no matter how we squeeze the system, it still operated. We could severely constrain transmission, and then local resources pop up and fill in the gap with almost no change, no increase in the overall cost of the system. So not only were we able to go to very high levels of renewable resources, but the system was robust across a wide range of conditions. In terms of hourly operation, as I said, we went and we looked at every hour of the year. On the left side, you can see the conventional system. And the challenge for the conventional system is actually during the summer peak, where that spike at the top to meet peak load coming from lots of air conditioners and other uses has to be filled in with combustion turbines. Very expensive, only run a few hundred hours per year. On the right, you can see how the renewable system performed in the same situation. What you see is actually summer peak is not bad. During the summer, there's a lot of solar energy, which lines up very nicely with the amount of air conditioning that's out there. The challenge was actually in the lower right in the spring, where there are enormous solar and wind resources and not a whole lot of demand. And so there you actually have a problem of lots of ramping and changes in the conventional systems in order to back up and provide the flexibility that's needed. This map shows the transmission build-out. On the left, you can see that the model would like to use very low-cost wind resources from the plain states as well as elsewhere and put in long-distance transmission lines. On the right, you can see that even when we constrained transmission very severely, the system was still able to operate. Here's a map with the main system, scenarios showing the amount of power used across the United States in both generation and capacity. Every part of the country contributes. Here's the same map under constrained transmission. And what you find when you look in detail at the different areas, you find that they become nearly sufficient across the United States in their own local resource. Again, the US has robust, diverse resources. Here's the cost. The system operated. We could not break it. We ran it up to 80% in the hourly level 80% of all power in the United States coming from renewables with conservative assumptions about the cost and performance of those technologies using only today's commercial technologies. And what you find is that the cost went up with the mid-range projections of just over 2 cents a kilowatt hour, in line with and actually lower cost than many of the projections made by the EIA, EPA, and others as to how we're going to control carbon emissions out of the power sector. On the right, you can see a graph that shows the most important factor in determining these costs is actually the technology cost and performance improvement. And all the constraints that we put on it, transmission, flexibility, resource, had much, much less impact. Industry growth. We're currently, in the present year, at about 17 gigawatts installed of wind, solar, and other resources, so that puts us in the right neighborhood. We looked closely, and we did not find any insurmountable long-term challenges in terms of getting this amount of power into place. Benefits. On the left-hand side, you can see that 80% renewable use also led, both in terms of combustion and in terms of the full life cycle analysis, an 80% reduction roughly of greenhouse gas emissions. And plus, as Suzanne mentioned, problems in terms of water use for the power sector. This cut water use in half. Land use. Well, biomass takes a lot of land area, estimated in this model of 44 to 88,000 square kilometers. In comparison, currently idled farmland under the Conservation Reserve Program is 120,000 square kilometers. Now, in terms of actual disrupted land, wind turbines, you just have a small platform and you leave large spaces that can be used for farming and ranching around it. In terms of actual disrupted land, 4,000 to 10,000 square kilometers were used in these various scenarios. And the comparison I like is golf courses in the United States, 10,000 square kilometers. If we can do it for golf, we can do it for renewables. So key analysis results. Commercially available today, renewable technologies are more than adequate to supply 80% of total US electricity generation in 2050, while meeting electricity demand on an hourly basis in every region of the country. We need to have increased electric system flexibility to do this, but there's a whole host of technologies that we already know that can be moved into place to make that happen. And the abundance and diversity of US renewable energy resources can support, across this whole range of different constraints, it can support this kind of outcome. And finally, the direct incremental cost associated with high renewable generation is comparable to that seen in other studies for the cost of controlling carbon emissions. There's a long list of future work needed, sub-hourly work, wider range of scenarios, much work to be done in this, but it is really a tremendous opportunity that we see. As I mentioned, if you go to the website, you'll see a set of maps, and you can look in detail, real time, you can watch an hour-by-hour simulation of the entire United States grid as shown on the right. I won't get into that. Finally, let me just close with a statement from the President. We have a choice. We can remain the world's leading importer of oil, or we can become the world's leading exporter of clean energy. We can hand over the jobs of the future to our competitors, or we can confront what they have already recognized as the great opportunity of our time. The nation that leads the world in creating new sources of clean energy will be the nation that leads the 21st century global economy. That's the nation I want America to be. Thank you.